Hello, and welcome to the AQUALIS Sustainable Water Compliance Summit. This session is titled Stormwater Management and Maintenance in a Changing Regulatory Landscape. We apologize for the delays. We're having some technical issues on the back end. My name is Bob Crossan. I'm the editorial director for the Endeavor Business Media Water Group. To begin today, let me explain how you can participate in the event. First of all, if you have any technical difficulties, please use the Q&A box. You can put in your question there, and our technical experts will help you out. Additionally, you can also use that Q&A box to submit a question to our presenter, and we will answer as many as we can at the end of the presentation. I know some folks have been using the group chat or trying to answer some in there, but if you can please put it in the Q&A box, that allows us to track it so that after the event, if we haven't answered your question, we can get in touch with you to share an answer. Also, please be aware that today's event is being recorded, and you'll be notified via email when the archive is available. At the conclusion of the webinar, you will receive a link to download your certificate, which can be used to submit for credit with Stormwater University or to serve as a personal development hour for attending today's webinar. Certificates will be sent to attendees who viewed this session for a minimum of 50 minutes. For those viewing this session on demand, you will need to complete and pass a short quiz at the end of the session to receive your certificate link. Now, I would like to introduce our presenter, Dr. Francine Kelly-Hooper. She is the Canadian Sediment Lead for GHD in Waterloo, Ontario, Canada. She is a sediment subject matter expert with more than 20 years of international experience in circular economy approaches to contaminated sediment management. Francine has dedicated her career to finding safe, beneficial reuse alternatives to typical waste disposal practices. Her 7-year PhD research project from the University of Waterloo, Ontario, Canada, developed the biogenic interference calculation, or BIC, which eliminates the false petroleum hydrocarbon detections in organic soils, sediment, and compost materials. Her Canada-wide stormwater management pond sediment chemistry study and collaborations with all levels of government has led to the only beneficial reuse approvals of their kind. So from there, I would like to hand it over to Dr. Francine. Thank you so much for being here, and take it away.
Thank you very much, and thank you for the opportunity to speak to the group. And I'm hoping if anybody has any questions, they'll let us know either now or afterwards if they want to contact me as well. But I think I'll just get started. So this picture was taken in 2022 of a pond that should have been under 3 feet of water at least, so lots of sediment, and we're trying to promote more cleanouts for flood control purposes, water quality treatment purposes. The Ministry of Environment here in Ontario is very invested, very supportive of trying to find beneficial reuse options. They've built them right into our new excess soil beneficial reuse regulations as well. And things are continuing to develop, and I'm continuing to work with federal and provincial governments on developing new legislation and new solutions to the problem of how do you find beneficial reuse of sediment that's not perfectly clean. So I'm going to be talking about 2005 to 2025 Canada-wide stormwater management pond sediment chemistry survey. I started it when I had my own business, running it out of my own garage, and we had Canada-wide samples that began in 2005, and they continue to come in today. So also talking about the newest regulation that I just mentioned, and then I'm going to talk about some case studies on how total petroleum hydrocarbon forensics has been used to obtain approvals for beneficial reuse of asphalt contaminated sediment. Asphalt's going to be the key word during my presentation because, as I'm going to talk about, over 99% of our ponds fail beneficial reuse because of asphalt particles. And then TPH forensic source identification tools. And then also I'm going to talk about the U.S. ban on coal tar sealants used to blacktop and asphalt driveways. Anybody's interested, I have publications that I can share as well with the group. These 2 publications talk about the Canada-wide survey, 371 sediment samples collected from 121 residential/commercial swim ponds. And I'm going to talk about PhD research and ongoing regulatory collaborations. And what I've got here on the left, sediment sampling chemistry analysis was involved. I've also done years of both bench scale and field trials using earthworm and plant toxicity testing methods, and then also field trials, just to show that the sediment actually was a very good growth medium. And I'm not talking about, for example, sensitive agricultural food species, but if we're talking about roadside species, you can see from the picture on the right, and I'll get into it a little bit more later, the sediment, unamended sediment actually does quite well when you're growing like roadside grass species and trees. Okay, here we go. And in that one, the manual that I showed in slide 4 was written for the Toronto Region Conservation Authority. It's now being used across the province. Just to give you an idea of the data that I'm going to talk about as well, it supports the idea of when you're trying to determine how many samples to collect. Oops, something moved. There we go. Hopefully that's working. Okay, it's random. So in this case, what I'm going to show you there, the model that I've developed through all the chemistry data, which has always been collected inlet, center, outlet, it supports the idea that the number of samples and the sample location are not based on how big your pond is. It's actually based on, is there one inlet and is there one outlet? And what it's showing here for pond A, there is one inlet. Now, the idea is that if you have a fully developed watershed or subcatchment area, if it's had no actual spill events, documented massive spill events, and I do have one case study to show you of such a massive catastrophic event that demonstrates what truly contaminated sediment looks like. But if it's just like a residential neighborhood, it's been built up, it's just typical day-to-day use, there's no reason to expect there to be hot spots in the pond. And so what we're able to show is that if you do 3 zones, so collect multiple discrete samples within zone 1 inlet, for example, homogenize that sample for non-volatile analytes, and then do multiple discretes within the center inlet zone 2, and then the outlet zone 3 samples to be submitted to the lab. That would be enough to characterize your sediment. Also,
Francine, what slide are you on? The slides aren't advancing for the audience, so I'm going to take control over them for you. So if you could tell me what slide number you're on right now, I'll advance them as long as you cue me next slide.
Too bad. Okay, here. Let's just maybe back up to slide 4 if you can.
Yeah, we're on slide 4 right now. So.
Okay. Okay, so people got that. Did it move now if I use that button?
I think it moved now. There we go. That moved it, yeah.
Thanks. Sorry, everybody.
No problem. Again, technical issues we're dealing with, so apologies for that.
Okay. I'll just tell everybody that was what I was mentioning. The slide on the left, or the photographs on the left, are just talking about sediment sampling, chemistry analysis. The pictures in the middle were taken from my experiments that I've run on plant and earthworm growth trials, and toxicity and tissue analysis, reproductive. We did all the typical endpoint testing of swim pond sediment that failed for petroleum hydrocarbons due to asphalt. We also have in Ontario, of course, lots of road salt used in the winter, so salt is always elevated as well. But typical levels, everything grew really well. And then on the right, and I'll get into this case study more, just showing how well roadside grass species grew when they were simply hydroseeded on top of the material that was poured into pits. Okay, let me know if anything messes up again, but now I've advanced to slide 6. This is what I was showing with the sample zones. So the sample zone example in A on the left, that was the pond that had one inlet, one outlet. The pond to the right just shows another example where you have two inlets. That means that you increase from 3 zones to 4 zones. The idea is that each inlet receives runoff and contaminants from different subcatchment areas. So you should be zeroing in on those just to make sure that you're actually characterizing potentially different sources that might come in from those two different inlets. Okay. And again, this is in the publication that I put out there, but this is just a schematic, just to show what would be intuitive, I think, is that when you have the sediment coming in from the inlet, the heaviest sand particles will settle out first, and then as the lighter suspended clays and silts remain in the column, those move through the pond, and they will settle out more and more with the fines at the center and the outlet. Everything I'm talking about has an exception to the rule. I have found ponds that were maybe designed maybe 30 years ago, and they weren't designed very well, and so they can have sometimes like a bottleneck flushing effect where they actually push the heavier sand to the outlet before they settle at the inlet. If you do find heavier sand at the outlet, that's a pretty good indicator that maybe the pond needs a redesign, because they are designed to flow everything out from the inlet progressively to the outlet. But what I want to show with this slide here is that we did a statistical analysis on all of the data. We wanted to see if there were any significant differences in both particle size and contaminant levels within each zone. So what this is showing here in yellow, we're showing that the inlet sample zones have 39% coarse particles. As you move to the outlet, that reduced down to 28% coarse. And of course, as well, we know that the coarse particles tend to hold lower contaminant concentrations than the fine. And so we're just showing here the 8 analytes that actually did exceed regulatory limits. They were significantly different from the inlet to the center and from the center to the outlet. The inlet versus outlet, there were 17 analytes that were significantly different, meaning the trend was that there were far more significant differences between the inlet and the outlet. And that tells us that it was a gradual progressive change from the inlet to the outlet, meaning that the 3 zones for one inlet model actually did truly represent what the entire contaminant levels look like throughout the entire pond. I also want to mention all of the data that I'm talking about was collected with full depth core samplers, where we push down to refusal, and then we take that sediment. You can visually identify the clay at the bottom of the pond. That is removed from the sample, and what's left is the actual black, really soft material, gray to black, soft material that would have been the true sediment that accumulated after the pond was constructed. And that's where everything we do here, it looks at the entire volume homogenized, meaning if the pond hasn't been cleaned up for 15 years, that entire volume of sediment that you collected will actually represent what happened over the entire period of time, over all those years. So nothing I've done tries to look at the top layer, what happened 2 years ago. Everything looks at the entire lifetime of the sediment accumulation. And the reason for that is, of course, when the excavators get in there and they pull out all that sediment, they're not scooping off the top. They're collecting the entire volume. And that's what we really want to represent in terms of what does the final chemistry look like for reuse purposes. So sediment analytes that we looked at, as I mentioned, total petroleum hydrocarbon, 99% exceeded due to asphalt. We looked at polyaromatic hydrocarbons, which are an ingredient or a component of TPH. 65% of those exceeded, and I'll talk a little bit more about coal tar sealants as being a key source of PAHs in the asphalt mix or blacktopped on top of asphalt pavement. Metals, surprisingly for a lot of people, they're actually quite low. 10% exceeded, and it's usually zinc, sometimes copper, which is linked back to vehicle materials like brake pad dust, steel belted tires, that kind of thing. And then, of course, I mentioned road salt, analytes, 88% exceedances. The thing with the exceedances are the regulatory limit that caused that exceedance. Those limits were set here in Ontario decades ago, and they were really set for protection of sensitive agricultural species. And that's why, even though we get these exceedances of those really stringent limits, the roadside species that we use here in Ontario, they're very, very adaptable to elevated salt. So what our Ministry of Environment has done is they have put in place salt exemption rules where even though you're exceeding, you're still allowed to reuse in roadside environments. That's something else I haven't really mentioned. Everything we're talking about today is a circular approach, meaning if we can say that the sediment in that pond was contaminated by road contamination, then we're talking about reusing it back within a road environment, not structurally, but as a topsoil amendment, fill material, berm construction, that kind of thing. And we also tested for nutrients and particle size, something that might surprise people maybe. Nutrients are actually quite low in the sediment. They can be very high in the water column, but we're finding that available nutrients in the sediment are actually so low that if you want to make the sediment an ideal growth medium, we would actually apply 20% compost to try to bump up the nutrient levels. Haven't had to do that, as you saw with that picture, but just to let you know that nutrients are actually in the sediment quite low. Just highlighting asphalt, number one contaminant, which is good news because if I'll get into this a little bit more with the forensics piece, asphalt is, it's actually, even though it's a high TPH source, it's actually quite inert, not leachable, not bioavailable either. So you can find beneficial reuse options even though your TPH is high. Here's the rationale for this, and this starts to merge into some of my PhD TPH research that I did. But again, I'm hoping this might be intuitive to people that if you've got a liquid material, let's say gasoline or diesel, for example, compared to solids like tire rubber or asphalt, your liquid products are going to be have a higher water solubility and bioavailability risk than you would get from these solid bound up materials. So 99% of the sediment exceeded due to asphalt TPH contamination. The 2016 to 2020 plant and earthworm ecotoxicity tests of asphalt contaminated sediment, growth and reproduction were as good or better in the sediment mixed with 20% compost than they were in the actual clean control soil. And the earthworm tissue analysis did not indicate PHC uptake. One thing I was going to mention in terms of the growth and reproduction being better than in the clean control, Environment Canada has a prescribed recipe, if you will, of how you actually generate, I'm calling it clean control here, but it's called artificial soil, where you buy clay and sand and a certain amount of peat, and you mix that together. The artificial soil recipe is not designed to produce the absolutely perfect, spectacular results. What they're supposed to do is represent a typical, maybe a typical unamended soil that you would find on agricultural fields. And so our sediment mixed with compost actually performed better than the artificial soil. Case studies, asphalt contaminated swim pond sediment for beneficial reuse. So this was the picture I had initially. So this is case study 1, 2022. We had sediment reuse on highway right-of-ways in Ontario. Our Transportation Association of Canada issued the Environmental Achievement Award for this one. What we had here was our Ministry of Transportation was widening one of our major highways in Toronto, And they didn't realize when they started the project that they were going to have to do a clean out of 3 swim ponds that were right beside the highway. And there, I'm going to go here. There we go. So what happened was they were told that they were going to have to clean those ponds out as part of the highway reconstruction. It amounts to over 3,000 truckloads of sediment, and it's going to add $3.3 million to their waste disposal. I'm not talking trucking, I'm just talking tipping fees to take it to a landfill. Not to mention in Ontario, at least, we have a lot of pushback from our landfills. They do not want to take this material, and so what happens is a lot of sediment actually can't be reused unless it is bulked up with polymers, sawdust, other organic material just to solidify it. And so there was a lot at stake for the MTO to be able to find reuse options. And so we were able to truck half-filled dump trucks with undewatered sediment, and we had dug out these, there'd be 6 foot pits that you see here, 7 locations along the major highway, and we just took the sediment straight to those pits, dumped it in. Within 3 weeks, they were dry enough to walk on, and so this was actually worked out even better than we had hoped because it hadn't been done at this scale before. You can see 1 year later what the hydro seeding looked like. And this was without compost. This was just 100% sediment, just hydro seeded it, and it actually looked really good the following year. Case study 2, this was the very first sediment cleanout where sediment was allowed to be reused instead of disposed of in Canada. At that time, because our sediment was going to be reused on tree nursery, that was actually an agricultural zone, land use zone, not municipal, and so our Ministry of Environment could not approve it, but our Ministry of Agriculture, and we also have our federal food inspection group that was able to issue the approval to use the sediment as a topsoil conditioner. And so this was interesting because the Nutrient Management Act only allowed us to spread 4 inches of the sediment on top of this really sandy soil, very sandy soil at this nursery that hadn't been amended in the 30 years that the nursery ran. And so these are silver maple trees that were planted. On this side is where the sediment is, and on this side is unamended sediment or soil. So this is unamended soil, amended soil. Mark Sunk was the manager who approved this, and he's about 6'2", just to give you an idea of height. What we found after reusing the 60 truckloads of sediment was that the trees grew twice as tall, and they also, this is a November picture. You can see here the yellow leaves, they were changing color. We found that the green leaves over here showed that the trees were not only taller, they were also more tolerant to stress conditions. So it was a win-win all around for this particular project. Third project, this was the very first time the sediment was reused within municipal boundaries. And what we did here, we got really creative because there was no roadside reuse in this urban neighborhood, but the road that ran up the middle had actually, it had some really beautiful landscaping done in it. So we knew that whenever we have road construction, brand new roads, the specs say to bring in virgin, completely clean soil in terms of building the roads. So what we did was we dug out that perfectly clean soil in the middle of the road, the boulevards, took that wherever they wanted to take it because it could go anywhere. And then what we did was we refilled the area that was now empty. We refilled it with sediment, and then we went back in with landscaping species, and we replanted, and it actually took really well. So these are 3 of the top awards that we've won for 3 different case studies. Did that push to audience? Okay. I just want to make sure. Are you seeing slide 16?
We're seeing slide 16. Make sure you use the previous and next buttons. When you click on it in the side panel, it doesn't send that slide to them. So you have to click on the previous and next to push it to the audience.
Perfect. Thank you. This is, if anybody's interested, this is our excess soil regulation that we're working with in Ontario right now. Just as a side, a quick side, I do a lot of international work, and we have, especially there's groups in the U.S. as well as Australia and New Zealand that are looking at this legislation to see how Canada is trying to take not perfectly clean soil and sediment and safe beneficial reuse options as opposed to landfill disposal. Our newest legislation, when it comes into effect soon, it's going to say that you need to demonstrate why you're not reusing contaminated soil or sediment. And that means that the landfills have even more premise to refuse. And so it's really getting people to think outside the box in terms of how can we use safe, beneficial reuse alternatives to waste disposal. Now, I'm going to recognize up front these carbon ranges, F1 to F4G, that's a Canadian terminology. But the bottom line is for anybody who deals with hydrocarbons, what they do is they include the entire carbon 6, lightest carbon 6, which would be the gasoline range, all the way up to carbon 50, which can be analyzed by GCFID analysis. And I'm going to talk about that a bit more as well. Also, F4 gravimetric just means that after carbon 50, the material is so heavy and like a tar that now you actually have to weigh the extract because you can't analyze it through a GCFID instrument. And just to show you typical petroleum hydrocarbon products and where asphalt falls in here. Asphalt is, and I'll show that again, but it's around the carbon 22 range is where it starts. It doesn't have a super light, super soluble or soluble PHC fractions or TPH fractions, TPH, PHC, interchangeable for today's discussion. Oh, I'll back up a bit. So in our world, if you find C10 to 16 F2, that tells you that you're not dealing with asphalt anymore, you're dealing with a light petroleum product. If you're dealing with asphalt, you're looking for a non-detectable F1 and F2. So there's different ways that we look at this from the start when we get our chemistry results. So how do you know if it's asphalt or not beyond the carbon fractions that I just talked about? There are extremely highly specialized methods for sure that are used for petroleum exploration and for identifying sources, things like biomarkers, alkylated PAHs, for example. For today's talk, I'm actually going to show we never have to go that detailed. Our regulators, and again, I have international examples of how this is done, not just Canada. What we can do, though, is we can just use the bulk soil and leachable, TPH, PAH concentrations and distributions, and GCFID analysis and chromatogram patterns are all we ever use to demonstrate that this is asphalt. That's from the forensics piece, but also I'll talk a little bit as well about our precipitation leachate procedure that provides another safeguard to make sure that you're approving something that is safe and will not impact groundwater or be bioavailable for impact to human or ecological health. So TPH, just a little bit of, I'm going to say this would be high school level chemistry, just showing that TPH is a mixture of, can be hundreds of compounds. We have aliphatic examples on the left, and then we also have aromatic. The key here that I'm going to talk about later is polyaromatic hydrocarbons. Those are the ones that have been identified as toxic, mutagenic, carcinogenic. Those are the ones that we really do pay closer attention to if they are exceeding regulatory limits. So for anybody who doesn't know what chromatograms are, they are, when you analyze your sample, the instrument that the labs use generate these patterns on a laptop or on their computers. And each pattern is unique to the source. And these are just examples. Again, there's always exceptions to every rule, but for today's discussion, what I'm going to do is I'm just going to show you what I talked about earlier, which is the patterns in addition to the carbon ranges will be a good indicator of what your product likely would be. So in the case of what I mentioned earlier, which was diesel, this one is fresh diesel. This one's really weathered diesel. When you weather diesel, for example, the front end, the F2 range or the 10 to 16, those weather fastest. Bacterial decomposition, water washing, sunlight, all of those things combined they will target this lighter, more easily weathered fractions are in this end. So that's why they disappear first. And then you're left with the heavier, proportionately. You've got these heavier C16 to 34 range. It's not that it produced this, it's just that when this disappears at the front end, this is what you see afterwards. So in this case, the F2 or the 1016 is red. So you can see that there's lots of red and there's lots of gray, 16 to 34, in these products. Now, as soon as you start getting out of fuel, for example, and you start getting into motor oil, asphalt, and to some extent coal tar sealant, and as well organic matter, you're not seeing any red anymore. You're seeing here that it is actually dominated by this dark blue, that F4G I mentioned, the gravimetric weight, really heavy carbon range. And then when you look up here, you can see that dark blue is the majority of the sample, and that is your asphalt. So it will have non-detectable F2, some of the F3, and then lots of F4 and F4G. And in the case of coal tar sealants, you're going to find very little F2, and you're going to see lots of F3, and then some of the remaining F4 and F4G. That's what I want to talk about for that piece. But you can see visually that the shapes are very different. So in the case of a diesel product, you're going to have, well, actually any product that comes from a crude oil base, crude oil and crude oil refined products, will have what's called a unresolved complex mixture. That's a hump here. These humps that you see, those are a UCM, unresolved complex mixture pattern, and those are characteristic of a crude oil product. And you can see very, very distinctive humps. When you're dealing with a fresh product, you're going to see these evenly distributed result peaks. And then as soon as it gets extremely weathered, these peaks disappear first. And now you're left with mostly UCM and very little peaks extending across the top. Motor oil doesn't have result peaks, whether it's weathered or not. Weathered asphalt, again, it should be very smooth. When it comes to coal tar sealant, so different. Coal tar sealant, of course, comes from coal. Any coal product that you see will not have the UCM because it didn't come from crude oil. It will be flat. And then you will have many result peaks that are not like these here, evenly distributed. They're random. If you were to look at just the chromatograms, to the untrained eye, it might look like natural organic matter. In this case, it's peat soil. They can be described similarly, very flat, irregular result peaks, irregularly distributed result peaks. But you're going to find, if it's organic matter, the majority of the pattern is going to be on the heavier end, so C22 to 34, whereas the coal tar seal coat will be predominantly in the 16 to 22 range. Chromatograms, I know this doesn't look, this is kind of faint here, but what I want to show here is that you should always, always, always ask your lab to include chromatograms in your lab reports. However, you may find, in this case, it's the exact same sample, but what happened was the lab, the Y scale here is 4,000, whereas what my group does here at GHD is we take the actual software license that the labs use, and we get the electronic versions of their chromatograms, and then we reprocess them ourselves. So by reducing this 4,000 down to 160, now you can see the pattern. There's a lot you can do with it as well, but just so you see, always ask the lab for chromatograms, and you can ask them to adjust their Y scale so that you can actually see what you're looking at. Here's a case study I just want to show you of, it was an actual swim pond on the side of a highway, so not a residential neighborhood. And in this case, it was a terrible accident with fatalities, and 40,000 liters of diesel were spilled directly into a swim pond beside the highway. It ran into the pond, and then it discharged out through this creek. The initial first responding consulting firm ignored the pond. It assumed that diesel floats, and so they focused strictly on capturing at the outlet and pumping off the top to try to protect this natural habitat. But the problem was they didn't realize that even though diesel floats, diesel will attach to solid particles, so total spin solid, and it will settle out of the column and into the sediment in the basin, which acted as a sink of more diesel. No matter how much they pumped off the top, it would constantly resurface from the bottom up. And so we went in and we collected sediment to see, can we tell if there is pre-existing asphalt in the sediment combined with the diesel product, and that's what we wanted to do here. So here is the chromatogram. This is the other thing I want to mention is, I'm going to go back up. I'm going to back up a tiny bit here. If you combine asphalt and, let's say, weathered diesel here, what you're going to do is they don't change shape. They actually become a hybrid. And so you will have a distinctive double hump. You will have your diesel at the front end and your asphalt at the back end. So that's what you're going to see here. So what you've got here is the diesel at the front end, partially weathered because of the combustion. And then you've got the asphalt at the back end, and then you have a little bit of organic matter mixed in for good measure. And now you can see the light F2 end is showing up. You've got the red, but you also have everything else present. And that's represented by the fact that it runs all the way from C6 all the way to C50. And that shows up in your pie chart that you have a whole mixture of heavy and light products. So what do you do with this? I'm just going to show when you overlay everything, you can start to see what the pattern, like these are my control samples. So when you overlay the control samples onto your sample, in this case, the trucking company was trying to dispute that we could even tell what was in the pond before the accident happened because they didn't want to pay for the clean out of the pond sediment. But once we showed them this evidence, and we had some legal dispute happening as well, but everybody, as soon as they saw what I'm going to show you next, everybody kind of put their hands up and said, okay, fine, we'll clean it out, and they did. Okay, so when you combine these two, for some reason my animations are doubling up. But you're going to see, when you do that, you start to see the patterns that will pop out at you. Doubling up. Okay, now what I did as well, though, to drive my point home, with this particular client, it's a private highway in Ontario, I had already had 15 ponds in my database, so I already knew what to expect. This highway is mostly concrete, but has some asphalt off-ramps, but the cleanest ponds I've ever seen in my history of my career were on this highway. And that is because you don't have these kind of accidents happening all the time. And so in this case, I was able to go to an off-site pond, which is right here, and you can see no red, no light hydrocarbon. When I combine the chromatograms, you could see the asphalt was absent in this off-site pond, or sorry, the asphalt was present The diesel signature pattern was not. So we've talked about TPH risks, but what about PAH risks? And just talking about asphalt has very low, and in fact, that highway that I just talked about, the PAHs in their pure hot mix are completely non-detectable in pure asphalt. And in this case, the coal tar sealants, if anybody on the call knows about this, they are 1,000 times higher in PAHs than any crude oil source that you would look at. So PAHs are quite concentrated if you're dealing with coal tar sealants. Just showing you my point here is if you add up the total petroleum hydrocarbon concentration and then you calculate the total PAH concentration, in this case, 33% of the TPH was made up of PAHs, and then the pure asphalt was 0.02% PAHs. Also, you're really light two-ring PAHs, which would be in the C10 to 16 TPH range, non-detectable. And everything else, all of the other ring sizes were detectable. In this case, the two rings were detectable, but everything was detectable in the coal tar sealant. Just a quick slide just to show you, again, this is interesting to me because the United States has, for over 10 years now, I believe, they've been working through banning coal tar sealants. And there was a class action lawsuit for, I think it was like close to $1 billion, was brought against coal tar seal coat industry, where they wanted the coal tar sealant industry to pay for the swim pond sediment cleanout, saying you're the reason that our PAHs are a problem. That ultimately did not, that the suit was not successful, but it did put the spotlight on why it's a good idea not to use coal tar sealants in urban environments that are going to end up in your swim pond. Now, because of that study, the Minnesota Pollution Control Agency contacted our Ministry of Environment in Canada and said, hey, we're sharing Lake Ontario. We need you to get control over your coal tar sealants in your part of the world too. And so the Ministry of Environment paid to have me look at all my sediment to see if we could use the model that the Minnesota Pollution Control Agency used, which is the chemical mass balance receptor model. And that's what we did. They trained me on how to use that software, and then we ran it against all of my samples, and it came back that coal tar seal coat was always the dominant factor in whether our PAHs were high in our samples or not. So TPH and pH leachability tests are, in my work, I always require them to evaluate beneficial reuse risk. So you've got your bulk soil testing of TPH and PAH, and bulk soil testing methods globally, they use very aggressive extraction techniques. So solvents, and you can use heat, you can use shaker methods, but the idea is to make sure that regardless of what the matrix you're testing is, or how tightly bound TPH and PAHs are, the bulk soil testing will quantify everything, whether it's soluble or leachable or not. Whereas when we work in the, it's a simulated precipitation leaching procedure, SPLP, that test uses just neutral water, percolates it through, and tries to say, okay, if we use this sediment and it rains, what's going to happen? What is the risk of leachability and bioavailability if we use it? And so we take the bulk and then we also combine it with the SPLP testing. And so over 100 sediment samples have been analyzed for the SPLP testing. Every single sample I've ever tested had non-detectable TPH in the leachability results. Now, I just want to qualify that by saying the TPH detection limits are around 50 milligram per kilogram, okay? So very high relative to PAHs, which are usually around 0.05% milligram per kilogram. If you lowered the TPH detection limit that low, you would have detectable TPH, I'm guessing, to some extent in your results. But I'm just letting you know that 80% of our samples also had non-detectable PAHs, but samples that had coal tar sealant in it at very high concentrations, they did show detectable PAHs. But generally what I'm finding is that whether it's asphalt or coal tar sealant, as long as it's in a solid form, very low risk of leachability and PAHs regardless of which source it came from. It's just that the coal tar sealants they cause more risk discussion, and it takes more effort to get the approval. But it's extremely rare in my experience that even if it came from coal tar sealant, that you couldn't still find some reusable options that would be very protective of groundwater and ecological systems. So this indicates that bulk soil analysis had overestimated solubility and regulatory exceedance risks, and in most cases, risk-based beneficial reuse options are possible. Conclusions: 99% of my sediment samples failed background TPH regulatory standards due to asphalt. 65% failed PAH limits due to coal tar sealant. Leachability and toxicity testing indicated low bioavailability and beneficial reuse risk, and risk-based beneficial reuse as landscaping material has been approved within roadway and also recently industrial environments. So thank you very much for your attention and your time.
Thank you, Francine. And we have a little bit of time here to do some questions. We've got to the bottom of the hour, so we got about 9 minutes or so. So I'm going to go through a couple of them that came through while you were talking. Here's one. Has there been a study on design approaches that slow down the turbulence, such as berms between inlet and outlet zones in the pond?
There are. I'm not an engineer. I just want to make sure people know that, so I'm not involved in the design. But yes, I can tell you any number of engineers here that would design baffles in to try to slow things out and allow the sedimentation faster.
Yeah. This question, I'm not sure which slide this was when it was submitted, but it said, what about 6 ppd? Any monitoring for this?
No, not yet.
All right.
Good question.
Yeah. You mentioned, sorry, go ahead. I keep on talking over you. I'm sorry.
Well, things will keep evolving, right? Because we have PFAS is being raised. We also have microplastics being raised. We also have the tire contaminant that's being red flagged as well, tire rubber as well. And tire rubber, just quickly, the species that are being highlighted for tire rubber contaminants has to do with sensitive cold water fish species. I'm never a proponent of reusing contaminated swim pond sediment as lake fill or ocean fill material or land reclamation. So that particular endpoint is not an issue when it comes to tire rubber. I thought I'd raise that because that comes up almost every time I talk about this.
Interesting. You mentioned PFAS there. There was a question here about PFAS. They said, how do these methods of reusing contaminated soils influence? Oh, sorry, this is PSAAs. Sorry, I glossed over on it. But still, valid question. How do these methods of reusing contaminated soils influence PSAAs?
All I can say is stay tuned because it's coming.
You mentioned the high salts and contaminants were fine for their roadside vegetation. What kind of vegetation was that? Is it native or non-native?
We always use native, and they would be like perennial ryegrass, fescue, just sedges, things that you would normally see are very hardy in roadside environments.
Okay. Were there any toxicity tests done in the surrounding waterways to see if there were any adverse effects on nearby aquatic habitats or life?
Does that have to do with the swim pond discharges or beneficial reuse?
They did not clarify that. If you'd like to clarify that,
Yeah, so anytime I have reuse, is always at least 30 meters from a water course. It's also, the sediment is always planted, so there's not an issue or a risk of the sediment running off into a receding water course. Now, I could spend another hour talking about the other question of what about the recipient water course? So our ponds here are designed for 80% TSS removal, meaning 20% at best is removed. Worst, of course, is as they fill up and they start discharging more TSS, there's a greater impact. I ran a study in 1989 where I did measure how far downstream in a sensitive aquatic habitat was being impacted by a pond that was functioning as it should. And we were able to just show, yes, there is an impact. In this case, it was about, I know I'm doing metric, but it was about 500 meters downstream. We ran into, I did a lot of benthic studies. We ran into shifts from like caddisfly species, for example, stonefly species upstream that operate with gills and they're crawlers that need clean substrate to function. Immediately downstream, we're into earthworms, or not earthworms, bloodworms, that they're the burrowers and they don't have gills. And so all I can say is there is a definite impact every single time you put a swim pond in that I've ever seen to the recipient water course.
Okay. Got another here. Were there tests done over time to see if the pollutant load had been reduced from biological action?
No, no, no. We haven't looked at that before.
Do you have any
is that
information? Sorry, go ahead.
when you're dealing with asphalt, especially in anoxic environments, there's not a whole lot of opportunity for degraders to break down asphalt in cold anoxic environments. But having said that, I have run phytoremediation trials and we take the sediment out and we plant it with specific species. And we use seeds that were treated with a particular bacteria that were known to degrade hydrocarbons at like crude oil contaminated sites. And so I have actually seen data that shows that the hydrocarbons can be degraded in terrestrial environments when they're planted with the right species.
Okay. Okay. Do you have any information on correlation of the sediment loads with rainfall amounts and watershed or sub-watershed areas that contribute to the sediments?
I did all that with my ISCO sampler and catching first flash by headlights at 2 in the morning. But that's the extent of my experience with it. I have looked at that since. That was, I'm going to say 15 years ago, I looked at that.
Okay. What is the... Sorry, go ahead.
As long as the subdivision is finished and built up and planted, I don't think you can expect a big difference from one subdivision to the next.
Okay. Okay. What is the criteria for weathered versus fresh?
I wish there was a difference, and I'm working towards it, but there is no difference. Even though the toxicity is incredibly different from fresh to weathered, regulatory limits don't consider it currently.
Interesting.
These are great questions.
Well, there's a lot of very intelligent people who are watching right now. So,
Yeah.
and I think this will be the last one that we can have before we have to close out. But they are asking, have you partnered with U.S. agencies for reuse in the United States?
I'm wanting to. I believe the Army Corps of Engineers, I was told they've got programs that might be interested in working with me on these things. So anybody has suggestions or connections, please do. Please let me know. My email is right there, and I would love to hear from people.
Yeah, jot down the email and take note of it. Well, with that, I'm afraid that we have run out of time. So for those questions that we didn't have time to answer, we'll get back to you via email. Just as a reminder, at the conclusion of the webinar, you will receive an email with a link to download your certificate to use for Stormwater University credit or for one personal development hour for attending today's webinar. And that concludes the presentation. I'd like to thank Dr. Francine Kelly-Hooper for participating in today's event, and of course to everyone for joining. Don't miss our final session titled Our Closing Keynote, Alexandra Cousteau. You can join the session by exiting out of this event and going back into the agenda. Select the session by clicking on the View Session button to attend that one, and we'll see you over there.
Thank you.